Hi, I'm Pat Hindle with mmWave Journal. I'm here at IMS 2019 in Boston, talking with John Coonrod of Rogers Corporation. So why are the more diverse materials needed to meet the 5G demands?
Well, actually, I'll answer that a couple of ways. One, to begin with, just a simple answer anyway, is that, of course, 5G networks are far more complex than 4G, and just by the nature of that, the circuits that make up those networks are more complicated, and because of that, they can't do some of the tricks they may be able to do done in the past. And just as a quick example, in the past, something like 4G or some of the earlier networks, they were able to maybe combine a power amplifier circuit on the same RF layer as an antenna circuit or feed lines for the antenna. But now with the 5G being a lot more demanding and the more functionality needed, what they've ended up doing is actually having to separate the circuits. So the circuits are using a specific material that's optimized for that circuit function. So an antenna circuit would be using a material that's optimized for antennas. Power amplifier circuit would be, materials that would be optimized for power amplifier. So now in the past, what they were able to do, they may not be able to do now with 5G. It's either separate circuits, or it could be that the multi-layer circuit becomes more complicated. That one layers maybe the antenna with the feed lines and the radiating structures. Another layer of RF the same multi-layer circuit might be a power amplifier. So in general, the diversity of the materials is really necessary just because the functionality of the circuits have become a lot more enhanced and more critical.
So given that 5G has the two frequency ranges, FR1 and FR2, how does that affect the material selection process?
Yeah, that's good to think about actually, and I'll probably answer that simply to begin with and then expand on it a little bit. But to begin with, if you just look at a design, RF design at lower frequency versus higher frequency, there are certain aspects that you really have to consider for materials. And at lower frequency, let's say sub 6 gigahertz, generally the designer can use a thicker substrate, so the circuit itself can be a thicker substrate. And the thicker substrate allows them to do a lot of things. One is they get lower insertion loss, they also get more consistent phase response. Then when you go to millimeter wave frequency, just by the nature of having higher frequency, shorter wavelength, what happens is you really do need a thinner circuit. Not that the designer wants that, it's that there's unwanted resonances that can happen if the circuit's too thick. So they're kind of forced into using a thinner substrate at millimeter wave frequencies to reduce spurious modes, spurious wave propagation modes, radiation, things like that. So that they're kind of forced to use thinner substrates at higher frequency. Thicker is better, so they use that where they can at lower frequency. And along with that, there's another property that's substrate thickness related, and that's copper surface roughness, which is a topic we've talked about many times before. And at a lower frequency where you can use a thicker substrate, the copper surface roughness really isn't that impactful because the copper planes are farther apart. So when you go to higher frequency and you're forced to use a thinner substrate, now the copper planes are closer together and now the surface roughness is more important. So kind of as a general statement, but it does apply to 5G, lower frequency, thicker substrate, higher frequency, thinner, and then the copper surface roughness also comes into play as well.
So you recently did a study on plated through holes in the wall surface roughness, specifically for 5G. Why would you look at that?
Yeah, actually it's really because one of our materials that's been the dominant player in the 5G industry for antennas and actually other aspects is the RO4730G3 materials. And that material has an unusual filler. The filler is actually a hollow sphere filler. And just by the nature of the way the filler is, when a plated through hole fabricator drills the hole and then plates through to make a plated through hole via, they get a rough wall of the plated through hole. It's just the nature of the material. And what's happened in the past is some of the fabricators would look at the microsection and go, that doesn't look right. So we went off and we did studies on the fabrication side, and we also looked at the reliability, multiple lead-free soldering, things like that. And then when the RF designers looked at that and they got to thinking, I know copper surface roughness does make a difference in a planar way, so maybe copper roughness makes a difference in the plated through hole. And so that's really what sparked my interest. And actually, if the viewers are interested, I have a more detailed articles actually in mmWave Journal's December magazine. And that really does detail the study in more detail anyway. But really what I came out of that was I did evaluations of materials that had very smooth through hole wall and then the 4730 with a rough through hole wall. And I really didn't see a difference in RF performance.
Well, we really appreciate you talking to us today.
My pleasure.
Coming from IMS 2019.